In 1909, to investigate atom structure, Ernest Rutherford directed his students to carry out the famous Rutherford's experiment. A good way to investigate the structure of a microscopic system that is too small to observe directly is to send fast-moving charged particles into the system, and then look at these charged particles as they come out of the system. Rutherford used the newly discovered alpha particles coming out of a radioactive material. The experimental setup is like this. The alpha particles can only come out of this lead block through the narrow gap over here, and then they would go through the slit and hit a very thin gold foil. There's a cylindrical screen all the way around. The screen was coated with fluorescent material, so it lights up every time an outgoing alpha particle hits the screen. What Rutherford found was that most of the alpha particles passed through the foil unaffected, as if the foil was not there. Only about 1 out of 8,000 alpha particles were deflected at very large angles, some even nearly back in the direction from which they had come. These experimental results led Ernest Rutherford to publish his planetary model or nuclear model of atoms in 1911. He proposed that an atom has a structure similar to that of the solar system. The nucleus is like the sun, and the electrons orbit around the nucleus like the planet orbits around the sun. He said that because most of the alpha particles went through the foil unaffected, the atom must mostly consist of empty space, just like our solar system. It was known at the time that alpha particles are positively charged, and each has a mass about 7,300 times that of an electron. It was found later that alpha particles are helium nuclei. In any case, because when those very few alpha particles hit the nuclei and get deflected, they tend to bounce back at large angles. And because alpha particles are much heavier than electrons, this means that the nuclei must be even heavier, and because the alpha particles did not get attracted and pulled in by the nuclei must be positively charged. So Rutherford said that an atom has a nucleus, and the nucleus is positive and has over 99.9% of the mass of that atom. And the atom is mostly empty space, with the electrons orbit around the nucleus. Everything seems a perfect fit because the attractive electric force between a negatively charged electron and a positively charged nucleus is just what's needed to provide the centripetal force to keep the electron in circular motion. The only thing is that, at the time, scientists already knew that an accelerating charge gives off electromagnetic radiation. This means the orbiting electrons with centripetal acceleration can lose energy to EM radiation, spiral inward, and plunge into the nucleus in a small fraction of a second. In fact, it's about 10 to the negative 9th of a second. This means the atoms in Rutherford's model are very unstable, which contradicts the observed stability of atoms in nature. Even if we ignore the stability problem, Rutherford's model is still lacking in the explanation of the discrete line spectra produced by atoms. Because when an electron spirals inward, its orbiting frequency would increase continuously, which causes the EM wave given off by the electron to increase in frequency as well, thereby producing a continuous spectrum instead of a discrete one.